One, by listing all its elements. Two, by giving a definition of what belongs in the set. So that is extensional and intentional. Extensional is giving the list of all the elements that are in there. Intentional means we create here axioms, a formal description of what belongs in the set. And of course, the approach that is taken most is the second one, intentional. We describe what belongs in the set. So then a formal specification. What is a formal specification? So first of all, you have to know there are two kinds. You have informal and formal languages to describe specifications. So a formal specification is a specification in a formal language. The language we all use, the language I'm using now, is natural language, and that is an informal language. Why? Because it contains ambiguities. It has ontological deficiencies. What we're trying to achieve, the end goal of all ontologists, is having a formal specification, meaning a specification in a formal language, such as first-order logic. You might have seen this in a course. Not? Have you had logic? No. And then we have web standards like RDF, RDFS, OWL, programming languages even. There is also a specific visual language based on UML for making formal ontological specifications that is called OntoUML. It was developed by Giancarlo Guisardi, and so it has its own methodology, its own tools for developing ontologies. You can find all the documentation about this in the appendix. So then the reason why I moved back to the first definition, although I have liked the second one more for a long time. So are ontologies inherently shared? The answer is no. Because you start with a conceptualization. Conceptualization is one person's view of the world. That is where you have to start. So in the first instant, an ontology is the representation or the mental model of a single person. And then he can start checking whether this actually aligns with the mental model of other people. So therefore, you can create your own personal ontology. And it's a valid ontology. So for example, if you take J.K. Rowling, she had a Harry Potter world ontology in her mind when she wrote the books, even before the first one was published. So she had her own mental model of the world before sharing it with the world, basically. So that is also an ontology. But of course, ontology only become really useful or useful to us when they are shared. Because then we can establish a shared understanding. So what we're trying to do then is define what's called a lingua franca, so a language made for sharing. But you have to be careful with this concept, because it's not because you have an ontology that you have a shared understanding. So having words with a single definition doesn't necessarily mean that we all understand the same words the same way. This understanding is called ontological commitment. So you have a language. In that language we have words, we have symbols, and each of us has to understand those concepts, those words. That is establishing ontological commitment, and ontologies become useful when this is shared. But in reality, this ontological commitment is never shared for 100%. So there's always some slight misunderstanding, and so we have to be very careful with this. an extreme case. So then it is said that shared ontological commitment is at best partial. So you can never, although you have the perfect ontology, you can never assume that having the perfect ontology means having a perfect understanding, having a perfect shared understanding of the concept. So you have to be very careful there. And a very extreme example of this is a Japanese tale called the Konnyaku Mundo. It's a tale about a melon farmer that is quoting a Buddhist temple and a visiting Buddhist monk that is visiting the temple. And the melon farmer pretends to be a monk. And in order not to expose himself as being a farmer, he refused to talk. And they use sign language to communicate. And so the monk asks the farmer about the state of the world. The farmer thinks that the monk is insulting the size of his melons. So he responds in sign language, and the monk leaves, the actual monk leaves. And goes people in the village to tell that he's not qualified to discuss with such an excellent Buddhist guru. So actually, both people share the same language, the sign language, but had a completely different understanding of the language. The farmer was thinking that the discussion was about melons, the other one was thinking it was about Buddhism. So this is a very short description of the language of the tale. You can read it in the references there. But so ontological commitment is something dangerous as well. Having a language does not necessarily mean having a shared understanding. But suppose we have a decent level of shared ontological commitment. Then what are ontologies good for? There is some literature about it. One, it's very good for having computer-computer interaction, meaningful computer-computer interaction. Why? Because computers don't have conceptualizations. They use sign systems, and they combine formal symbols into new symbols and so on. So then having a shared sign system is very useful for establishing system interoperability. Systems that use the same words can communicate with each other quite easily. So then we have the semantic web as an application, we have core vocabularies as an application, formal specifications or ontologies as formal specifications for human-computer interaction are also very useful. Why? Because again, we can use fixed terms to communicate with a computer, and we can describe exactly what the computer will be looking for. So it's very good for information retrieval. So for example, I had a master thesis student that wanted to replicate a systematic literature review on enterprise architecture implementation. And so there was systematic literature review that was 5 years old, and he wanted to repeat that, so 5 years later. In a systematic literature review, you have to define your search queries. So then you have to use words. What he found was that in the search queries that the authors used 5 years ago, there were words that had synonyms that they did not query for. So then he developed his own ontology, saying, okay, we have this term that has been used in the initial study, but actually you have equivalent terms, and I will redesign my queries in such a way that I also look for those terms in my new literature review. So then ontology and structured knowledge about the world can help you improve your information retrieval. And it's also good for knowledge representation. So when you represent knowledge, when you have a definition, so for example in the standard, when you have a formal definition of a concept, it's very easy to say, okay, if I have this concept in one document, then this is the meaning of it. And then finally we have specifications for human-human interaction. And there the findings are that actually formalization is a bad thing for utility. Because if you have a formally defined language for human-human interaction, then the investment that humans have to make to understand the fully formalized specification is very high, and typically people don't do it or they do it partially. Then if you have an informal specification, like a dictionary or just a glossary, it's as useful and even more useful. Why? Because the investment for the people is lower. So then if you have meetings with people, it can be useful to define your ontology of the meeting, but then don't do a formal specification, just have a glossary or a dictionary. So for example, I believe it was 3 years ago, I worked for a company that also does consulting. And so then my new colleagues came to me, okay, so what are you? So I'm a professor, and what is your research? My research is on ontology, but yeah, what is ontology? Well, I'm trying to establish common understanding between people. And then they said to me, okay, actually, so after a few days, and they came back to me and said, actually, after having this discussion, I realized that in meetings, we lose lots of time on semantic discussions. So people start arguing, and after half an hour, they realize that we're actually trying to say the same thing with different words. Or people have a meeting, agree on something, come back a week later, and then they find out that they did not do what the other expected. Why? Because they did not have a shared understanding of what was expected. So then having this ontology of your meeting is an investment at first, because you have to spend time on defining your vocabulary, but then it's an investment. So there is return on investment once you start using it. So then informal specifications for human, or ontologies for human-to-human interaction are also useful. There are even more claims about the usefulness of ontology. You can find a few of them in an article on Forbes. But for those, there is insufficient academic proof at this point. So I'm not saying they're not true, but there is insufficient proof at this time. So then there was the notion ontology. I'm going back to the GUA and LEAD duality. So we said, okay, we have ontology, we want to define it, we want to use it in academia and industry. But actually, how does this work? How do we do the research together? So we apply a research method that is called action design research. And action design research is a research methodology that combines two different research methodologies. It combines design science research with action research. Design science research is like engineering. So you start with a problem, then you try to solve the problem, you test it, you have findings or results, and then you go back, you have either a new problem or a solution. When you have a new problem, you try to fix that, test it again, and you have an engineering cycle until you end up with a satisfactory result. That is design science research, but design science research, as it has been described in my domain, is weak on the evaluation. So it's like we test this once, or with one company, or with one client, and the client was satisfied, so we're fine. So this is a very academic approach, saying, okay, we as professors are the source of all knowledge in the world. We define our own problems, we solve them, and then we check whether there is someone in business that thinks this is useful. If there's someone that says yes and uses it, we're fine. Action research is the opposite. So then we go into practice and try to improve what happens in reality. Without scientific background, if you go to the extreme, we just try to improve what happens there. So it's basically consulting. Action design research is doing both at the same time. So we have the systematic way of solving a problem from design science research, and we have the intervention in real-world setting, not just one test at the end, but like continuous collaboration of action research. So then action design research has an engineering cycle that is called the building intervention and evaluation cycle. And it does what it says. So you start with building a solution to your problem, then you intervene, so you go to your company, test it there, you have results, you have feedback, you incorporate the feedback, you go back, building an improved version, and then you loop continuously until you have a satisfactory result. But you do this in the factory, not in a laboratory, not at university, and then going back with the final result. Company. So you do this in collaboration with the company on site. So then, what are the aims of this methodology? One, we're trying to construct rigorous artifacts. An artifact is then a solution to the problem at type level. Type level means that it is not only relevant for the one company you've developed it with, but also for other companies. So that is the academic part. You should be able to teach your results. They're at the type level, and then some other people should be able to learn from them and be able to apply them again in another setting. So that is the academic level. Type level solutions, generalizable and rigorously constructed. Rigorous means based on academic literature, based on academic methods. At the same time, this has to be relevant and applicable in industry. So that is then the instantiations of the type level solution. So we go to one or more, typically more companies, and we test our type level solution, whether it holds there. If it doesn't, we go back, we build a new one, intervene until we have a better result. So this leads to this model. It's a generic model of action design research. So we start with a problem formulation. In there you have two possibilities. You have practice-ingrained research, practice-inspired research, and theory-ingrained artifacts. The practice-inspired actually means someone from industry has a problem, goes to the university, goes to a professor and says, okay, could you help me with this? It's academia as a consulting company, basically, or the professor or the researcher as a consultant. Second one is theory-ingrained artifact. So that is more design science research. It's an academic that says, actually, I observe an issue in industry and reality. I would like to fix this. And then test it in reality whether it actually improves the situation. So the two different versions of this problem simulation depend on where you start. It's a problem discovered in industry, or it's a problem discovered in academia. So then after that, you go and reflect on your problem, try to come up with an initial idea for a solution. So typically, as academics, we go into the literature, we study what has been done before by other academics, see whether that can be used to solve the problem. And once we have an idea or a plan for a solution, we can start building, intervening, and evaluating. That is the engineering part of the solution. So we build an initial version, we test it. In reality, we evaluate whether it's good enough or not. If it's not, we take in the feedback, build a new one, and so on until we have a good product. And the last step is formalization of learning. That is again a very academic step. That is the generalization. It has worked in practice. Typically the practitioners are okay with it because for them it works. But of course as academics we want a type level solution. So then we have to summarize what happened in different companies and try to generalize the findings and publish them. So we have different models for this. So this is the IT dominant building intervention and evaluation cycle. The IT dominant one is actually the academics dominant one. So then that's a professor that sees a problem in reality, tries to fix it, and then goes to practitioners to solve it. First, it's with a few practitioners. Then once the product is sufficiently mature, we go to end users and try to have like a university spin-off. Unfortunately, in most academic, or the KPI for academics basically is publications. So after the first cycle, it's called the alpha version here, we have a test that it works, and most academics stop there. It's published, it's good, I'm fine with it. It's only when you start like thinking about commercialization and having university spin-offs that you go on with the beta version. But so that is something, yeah, it has to do with the way that professors are evaluated, but the methodology is able to support actually commercializing academic findings in the end. Of course, when you have a question from industry, the end goal is having or applying it in industry. So then the cycle is completely different. So then you have a question by people from industry, they go to academics or they consult academics for finding a solution, then they implement this in practice. If it works, it can be replicated in industry infinitely. So then what does the Global University Alliance and LEAD does with it? So actually GUA and the Global University Alliance and LEAD are like two sides of the same medal. So you see the two sides. One side is academia, one side is industry. So in the industry part, you see that people from industry develop artifacts, such as reference content. We'll come back to the reference content later. So reference content is things that can be reused. So project documentation or ontologies that can be reused. Then they actually use it in practice. Then from the use, they have feedback. And then with the feedback, they try to improve. When they can do the improvements themselves, then they do it themselves and go back. And you have the small loop on industry. So they have feedback, describe new concepts, develop the artifacts, and so on. Academics can study this. What happens in industry? That's one way of applying this cycle. Second is, sometimes the people from industry meet problems that they cannot solve themselves. Then they consult the academics that study the patterns in documentation, or go into the companies and look what happens, try to intervene, try to solve the problem. And then that research is, of course, so observing what happens in practice is research. Studying the patterns of what goes wrong is also academic research. And intervening, so the action design research part, is also academic research. So this is then a model in which you see how industry can feed academic research and make sure that academic research is relevant, not something abstract, completely irrelevant for industry, but actually very useful for them. So then, how do we try to achieve this cycle with Global University? Yeah, I forgot to say that. So the community of academics in this cycle is called the Global University Alliance. The community of industrial partners is called leading practice. So that is the GUA lead part. GUA is academia, lead is industry in there. So you have two groups that collaborate but have their own subgroups, let's say. And this model describes how they interact with each other. So then, how do we try to structure this collaboration? Solution is with ontology, and actually with many different kinds of ontologies. So we have defined an ontology stack. So it's a stack of ontologies of which the concepts are reused in lower level ontologies. In the past, I've referred to this principle as like it's invented by Nicola Guarino, this approach, and I've referred to this as Guarino's Aufbau Principle. Do you know what the Aufbau Principle is? It's in chemistry or physics. So it has to do with orbital theory. It's if you have a new electron, in which orbit do you put your electrons? If you have larger atoms, they have more electrons, and then so where goes the next electron? That is described by the Aufbau theory. When you make molecules, also you share electrons, then the question is again, where do you put the electrons? Well, that is also described by the Aufbau principle. So then this is a little bit the same. It says, okay, if I have a concept, where does it come from and where does it go? Where do I have to put my next concept? I've also referred to this as ontology weaving. So weaving is you have orthogonal threads and you try to make a fabric with it. So the weaving applies to or refers to the combination of domain ontologies and task ontologies into application ontologies. So you try to reuse orthogonal ontologies and try to make a fabric out of them at the lowest level. And then you reapply the same patterns over and over again to have new patterns at the application level. How this is done will be described probably after the break. So first a little more theory. So the highest level in our ontology stack is a top-level ontology. A top-level ontology describes very generic concepts. Actually, it's the most generic ontology you have. And it actually describes how you should describe other stuff. So top-level ontology describes primitives that allow for defining very generic or general concepts like space, time, matter, object, event, action, and so on. So in GUA lead, we use the OMG's meta-object facility. Do you know what Mufe is? No. You've seen UML? Actually, Mufe is the foundation for UML. So UML is an OMG standard. And actually, UML is described in Mufe. So Mufe is a meta language for UML, basically. And shows is, yeah, so if you read the, have you read the UML specification? No. So in there you find references to Mufe, and actually the language that is used to describe UML is Mufe. So it's a language about languages, basically. Or a language for describing languages. So think of it as like the grammar of your language. It shows what you can combine, how you can combine it, but not what you should combine. So then a level below those top level ontologies, we have foundational ontologies. Foundational ontologies are no longer about the language, but they are about the reality you want to describe with the language, with the language. Yeah. So it's actually your highest level of vocabulary. So then foundational ontology can be used to provide real-world semantics for general conceptual modeling languages, such as UML. And it also helps to constrain possible interpretations of their modeling primitives. Constrain, so the interpretations means, okay, this is possible in my model, this is impossible according to the model. So, because in your grammar specification, you don't say which sentences you can make. It's just how you can make a sentence. But then sometimes you can combine a verb with a noun and the sentence makes no sense. So what makes sense and what does not make sense is documented in the foundational ontology at a very high level. And then we reuse the concepts from the foundational ontology again in a core reference ontology. A core reference ontology adds a little more information, is a little more specific. And here you see the word reference appearing. So reference means that it can be used as reference content for other specifications. So you've seen the reference content here. It's in this industry cycle. So that means that where top-level ontologies and foundational ontologies are very academic, very abstract, here we enter into the real semantics of the business world. And here we have reference content, meaning that we want to promote reuse. So we have content that others can reference and that other content has to reference. So it provides a foundation for more reference content. So it's like object-oriented programming again. You have an abstract class. That abstract class can have subclasses. That subclass can have even more subclasses. And in the end, you end with your concrete class that has the properties from all the higher level classes. Typically, your concrete class belongs to the application ontology level, but of course it can reuse semantics from higher up the stack. So you have to think of it in this way. So it's adding more and more information until you end up into reality. Why adding those informations, or why adding that information stack level by level stack in the different stacks? That is to promote reuse and coherence across the stacks. Because you can learn from other applications in the same domain. We'll come back to that later. So then core reference ontologies is a standard used by different groups of users. So you have different users, actually different domains that will reuse the same semantics. So it's so in the core reference ontology you find words, you find meaning that is useful in different subdomains of your reality. For example, we have a core reference ontology for business. Then that core reference ontology can be used in sales, in production, in acquisitions, in finance, in accounting. Those are all subdomains of business, but when they need to talk to each other, they need a vocabulary that is not constrained to their own specific domain. That is what is in the core reference ontology. So that's cross-domain language with sufficient level of detail to allow for communication between different subject matter experts, but it doesn't have enough semantic richness to cover all the knowledge of a real domain expert. For that real domain expertise, you need something more that a non-expert cannot understand, and that expertise is documented in a lower level ontology. So then we go one level down, so then we've been we were here, core reference ontology. So the lingua franca between most people that have similar knowledge but not exactly the same. So then in there we split in two different types. We have domain ontologies and task ontologies. Actually, domain ontologies describe, that is the most popular term. So you have many domain ontologies. There are not as many task ontologies, unfortunately. So domain ontologies are more static. So they describe what is available, what exists, what you can use. A task ontology describes how you can achieve something. And then if you want to achieve something in a specific domain, you build an application ontology. So as you have seen UML, think of domain ontologies as like static diagrams, like UML class diagrams. Think of task ontologies as like behavioral diagrams, like activity diagrams, like sequence diagrams, and so on. So dynamics in task ontology, statics, infrastructure in domain ontologies. If you want to do something real, you have to combine. So domain, again, reference ontologies, document the expertise. Time for a break? Yeah, okay. Maybe we'll... it's better to stop here then. And then after the break we go focus on domain, task ontologies, application ontologies, and with an example on how to build them. Otherwise, if I explain this, I have to explain task ontologies and application ontologies, and that is more than at least 10 minutes. So
it's 3:15.
Yeah, indeed. So I'll give the break here then.
Thank you.
Okay, is it a 10-minute break?
Yeah.
Okay.
Yes.
Do you have a vending machine for water or?
I think so. We are doing very well. So
Okay.
I'm interested in exploring.
Okay. I think I need to do water. So.
Yeah. Sorry. I mean.
Yeah, but I didn't think you could do this.
Yeah. Just so we see in the room.
Yeah.
As well.
Nee, ik moet tot de conclusie komen dat ik eigenlijk een beetje mijn thesis aan het doen ben. Dat is waar, dat je, ik zei. Dat wel, maar mijn thesis was precies zo al vol met die dingen. En ik heb precies van, misschien moet ik dat ook niet doen.
Ja, dit is een beetje en iets zo verder en dan zo'n 3 papers zo.
Ja, dat is...
Ik denk iets ook echt wel vermelden, dat is het niet.
Zo. Nee.
Ja, ik ben van meerdere technologieën aan het beschrijven. Ik ben wel met het echt in verschillende benamingen technologieën. Ik ben wel aan het abstraheren, dus ja, dat is ontologie. Mijn thesis is niet zo zeker, maar ja, dus dat is interessant.
Ja, dat weet ik. Ik zit gewoon lekker. Dat is een beetje programma.
Ja. Dat is ook wel zwaar, denk ik.
Ja.
Het gaat juist spreiden over 2 jaar of zo. Ja. Het is super de pot.
Ja,
Dat is natuurlijk een pot.
Ja, dat is misschien... Ik weet niet wat het is.
Dat is misschien een beetje...
Zoals we het niet van hebben.
Dat is niet wichtig uit wat zijn. Nou, toen stoppen we. Ja. Ja,
niet zo lang, dus echt een week.
Ja, inderdaad. Ja, gewoon hetzelfde.
Ja.
Maar ik weet niet, zou dat toch niet
Nee, dat is wel.
niet zijn?
Nee, dat is wel
leuk.
heel waar.
Ja, dus dat is wat ik bekijk.
Ja, dat komt wel wel dat college maar dat is
niet. Ja, je had wel
maar
overschoten.
deze
Dus je bent echt in een bureau dat iedereen heeft.
het is wel een specifiek onderwerp als deze inspiratie te geven.
Dat is wel beginnen. Maar dat is niet meer
Dus we kunnen wel hier extra bij
elke maand wordt het nieuw gestemd.
Ja, soms je man zegt dat moet zo'n oude dingen gaan over de dag. Deze is heel wat onder, precies.
Ja, wat dat wel, dat is niet gestemd in de weken.
Ja, ik moet zeggen, dit is het academische stuk. En dat je dan zoekt naar praktische kanten, terwijl het is wat dus industrie en praktijk. Ja, dat is niet om te valideren door dat mensen te vragen. Dat is al heel streng gevalideerd. Ah, wel ja.
Iets intersectoraal, overwicht met.
Zonder alles in een
Ja, die feest, die dan.
We moeten niet doen.
Het zal ook niet aan boord zijn ook.
Dus ja, dat is zoals op school is. Ik vind dat er eens maar een agenda gezet. Ja, ik vind dat gewoon heel leuk. Ik heb een agenda gezet, maar ja, ik eens checken. Ik dacht, het is weg, maar ik ga er gewoon eens controleren. Maar het is gewoon niet.
Ik heb er vorige keer mail van gekregen van beter doen om te
Daar zijn we zo.
Personen eigenlijk. Nee, klanten of zo is dat enkel.
Dat is een enkel ding dan. Ik denk dat het
Ja, dat is iets
dat is
vaak.
altijd zo.
Ja, dat is gewoon. Ja, ik vind het
Als je
heel
niet
leuk.
console ding dan,
Het
dat
is
je
zonde, dat is
constant
toch
zo.
gaaf.
Ik hoorde het al bij een bedrijf en dat niet zo.
Ja.
Ik hoorde iets en al zeggen van ja,
Het is.
ik voorstel
Ja,
dat
het
ik
is
het
dan
zijn
wel
gedaan.
een veel zwaarder punt, maar het
Ja, ik heb een man op een vriendje gezeten in de eerste maand. Dat die man
Het is
dus
niet
ja, tegen
Het
dus
is ook niet per se
niet wacht tot dat plek.
zo.
Ik zeg, de eerste maand van deze week, dat is gewoon niks te doen. En dat is dan ja, gewoon de boekhouding bij het eigen bedrijf. Dus
Was dat er ook?
nee, maar niet zo.
Ah ja.
Weer als je het hebt verzand.
Ja.
Dus het is al echt zo. Maar ik heb er alles aan. Maar nu zijn we dit wel zeker. Ja, dat is echt zo.
Ja, ik heb het al als weekje gezien. Het is wel even dat je zit, je doet het kost zo, maar ik dacht zo lokaal of zo. Nee, dus dat is een beetje, ja, absoluut niet.
Ja.
Dat is juist, ah ja, dat is juist.
Maar die nemen mensen dan zonder elk.
Ja, ik weet het niet.
Ja, dat is niet.
Een functie.
Ja, het is gewoon het algemeen. Ah ja.
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 Ja. Druk je dit.
Ik neem ze dat aan.
Ja, je zou het ook wel. Die gewoon wel niet zo.
En dan is dat wel komen.
Ja, maar misschien wel het thuis, maar dat is de eerste maand.
Ook wel voor je moeder.
Niet door.
Sorry, ik was dus over dingen van Rowling.
Everybody's still here, so that means that you're ready for more, or do you wait another 5 minutes? We're fine? Okay, so we stopped at the domain ontology level. So everything above the domain ontologies is useful for standardization. So complying with the higher levels means that you reuse the same semantic information, that you have a common language. With domain and task ontologies, we're trying to diversify. So then we're trying to have something that allows us to cover the full richness of the reality in application ontologies. So that is why this was a good moment for a break. So we were about standardization, now we are about having real meaning that is directly applicable in reality. So then domain ontologies describe the vocabulary related to a specific domain. Again, what is a domain? It's universal discourse. So it's something that we think is a coherent set of concepts and relates to something, a practice in the world. Domain ontologies are only applicable to domains with a specific viewpoint. So that is typically the level where we have specialists. So specialist language, jargon, is something that you can call, that fits in a domain ontology. But this viewpoint on reality can be different depending on your domain. So, for example, you have different medical specializations, and every type of doctor looks at the person in a different way because he has all the knowledge. So all those specializations are domains. But then, if different doctors have to talk to each other across specializations, they need a core reference ontology. Think of that as a metaphor. Domain ontologies can also be used to develop domain-specific modeling languages. So those are modeling languages that are specifically designed to be used in a special domain. And then again, you can use UML and MOF to define your own modeling language. So have you seen the possibility of defining or creating domain-specific modeling languages, for example, with stereotypes? No. Do you have you seen stereotypes and tagging in UML? No. Okay. Good.
I think I may have mentioned the word in the systems design course in Systeemontwerp. When you put above the name of a class the keyword abstract, that would be a stereotype, for example.
Yeah, you can use those same stereotypes to have your own domain-specific modeling language, but then instead of using programming-related stereotypes, you use domain-specific stereotypes, basically.
If I mentioned it in one sentence. That was all. So.
Then next to domain ontologies, we have task ontologies. So then this is the dynamic part. Again, we have the same logic. So we have task reference ontologies. Again, the reference part means that they are there to be reused in applications. They describe the vocabulary related to a generic task or activity. Here, trivial examples like diagnosing, like selling. So how do I get things done? What is the sequence of things, or what do I need to do? What things do I can be forgotten? For example, those things are documented in the task ontology. So they are about getting things done. Then finally, with an application ontology, you're trying to solve a real world problem. So you're trying and you apply your knowledge of the domain and of the task you want to achieve. So think of it as like cars is a domain. So we have different kinds of cars, different types of models. Selling is a task. When you try to sell cars, we need the knowledge of what different cars we have in our catalog, and we need to now we need to know how to sell things. And then the application ontology is how do I sell these cars in the catalog. Okay, it's very trivial, but think of it as a metaphor. So the domain ontology is there to know what exists and what can be used in the application. The task ontology tells you how you get things done. And then, so in the task ontology, you fill in the domain slots to build the application ontology. If you look at it from the domain ontology perspective, you say, okay, this exists, and then you do the cherry picking. Okay, in this application, I need this from the domain knowledge, and that from the domain knowledge, and that from the domain knowledge, and then I'm done. So it's more specific, and I use the word cherry picking, so that means that you don't have to reuse all concepts from your domain ontology in your application ontology. It's the same with your core reference ontology. So you don't have to reuse every single concept from your core reference ontology in your domain ontology or in your task ontology. So you can really do cherry picking and say, okay, this is what I need for this domain or for this task. And then for your application, you do the same. Okay, from this domain, I need this for my application. From that task, I need that concept. But then your core reference ontology, make sure that everything fits together coherently. Because all concepts have been founded in this core reference ontology. And at the core reference ontology level, you also define semantic links between concepts that tell you how you can put things together at the application level. So that is a weaving part. Okay, one last section of theory. So in order to build those core reference ontologies from foundational ontologies, those domain ontologies from core reference ontologies, the task ontologies from core reference ontologies, and the application ontologies from domain ontologies and task ontologies, we need a few key principles. So here are a list of the principles that are used to do the development, to add more semantics to go across the layers of the stack. First key principle is a structuring orientation. Ontologies have what is called a structuring orientation. Structuring orientation means that they offer you a structure to better understand models. So here this is a very simple example where you use boxes to define fundamental meaning of a concept. So when you fill in something in the value architecture box at the conceptual level, okay, it means it's conceptual level object for the value architecture. So then you can use ontologies to structure your knowledge. To say, okay, I put this concept here, I put another concept in another box, and then by putting them in different boxes, I know that they have a different meaning. And then I know that concepts or things that I put in the same box have a very similar meaning. I know that things that I put in the same column share something. But since they are on different lines, there is also a difference in their meaning, in another dimension. The same if things are on the same level, on the same line, they share something, but then since they are in different columns, there is something different as well. So then ontologies can help you to define these matrices and so to bring structure into your knowledge, which makes searching the relevant things easier. Second principle used in the GUI ontology, but also fundamental in all applications of Guarino's Aufbau Principle, is categorization. Categorization is putting stuff together. Things of, yeah, different kinds, but that shares something. So like a trivial example is my belongings. They're not the same type. I have a bottle of water and I have a computer. They're not the same kind, but they belong to me, so that there is something they share. But it's not a semantic link. It's not that they are of the same type or subtypes of the same common thing. They're just completely different things that belong together for some reason. So it's a group. So like everything in this room is a category. So I put it together, and yeah, I would say I wouldn't know why, because there is no no property of the things themselves that makes them belong together. It's something else. No inherent property, of course, because belonging to me is a property. The opposite is classification. Classification is a more hierarchical way of putting things together. And that is like, yeah, classification, one of the best known classifications is that of all living things on Earth. So then you have classifications of animals, plants, fungi, and so on in different ranges, and so that is what is called the taxonomy. So you have like a supertype, and then below that supertype you have subtypes, and the subtypes have more subtypes, and those have more subtypes, and so on and so on and so on. But then, so this is not like categorization. There is a real reason why they belong together. The animals, they belong to the same, they have common ancestors, or there is genetic information that shows that they have something in common. So there is a reason why they are put together here. They belong to the same kind. You have kinds and subkinds and so on. Another way that classification is used in the GUA ontology and GUA and LEAD ontology is for part-whole semantics, or with part-whole semantics. So then we use the word classification for composition and decomposition as well. In other ontological domains, classification has only to do with kinds. So kinds and subkinds, and here part-whole relationships are also seen as part of the classification because they are have a hierarchy. So it's part is part of a whole, which can be part of another whole, which part can be, so I have a car, but in my car there is an engine, the engine has parts, the parts have parts, and so on. So that's composition and decomposition. But like ordinary classification with kinds and subkinds, this has a very clear structure. That is something that categorization doesn't have. So that is also why I use this graphic for categorization, just one big heap. And there's no real structure in the things you put together. There can be structure in your categories, but within the category there is no real structure. That is different here. In classification, and of course with composition and decomposition. So for example, with the nested dolls, that is also a very clear example of composition and decomposition. You have a doll that goes in another doll and another doll. Of course, in each doll there is only one at the same level. If you look at a car engine, the engine itself has many parts. So and then those principles are then used to create multiple levels in the layered enterprise architecture development method. So that is what LEAD stands for. So GUA is Global University Alliance. LEAD was an acronym that I haven't explained until now. So LEAD is actually short for leading practice. And in leading practice, the LEAD means Layered Enterprise Architecture Development. So then the layers are actually the layers you see here, but we don't, in those layers, so in the ontology stack, we only have classification of kinds. But in leading enterprise architecture, we also make layers with categories and with composition and decomposition. So that means that we have a multi-dimensional layering, which also means that it's impossible to show the complexity of the whole stack. Because you have layers for kinds and subkinds, you have layers for parts and wholes, and you have layers for groups and subgroups. And that structure and those layers with more and more detail are very useful to build your artifacts, but it's because they are multi-dimensional, it's impossible to visualize the entire or all of the complexity on a page, because that is only two-dimensional. So this is, for example, a two-dimensional example, but you lose part of the complexity. So the layering is more than just one or two dimensions. But the logic is always the same, so you reuse semantics, meaning, relationships from a higher level, you add more detail, and you use the detail in a lower level again. So again, it's like, as in object-oriented programming, you add semantics, you add more information, more detail, layer after layer. Okay, so now we move to a case. How can all those principles be combined into one and do something useful? Or can they be applied to do something useful? So one of the cases is the case of the Dutch railway company called NS. And first we had, there are a number of case studies. So here we have a list of case studies that have been published in the literature. So you have one of a Dutch railway company. That is the one I will discuss. And the goal of this project was to introduce Industry 4.0 and IoT logic in their operations. Another case study that has been published is a North American healthcare provider. I forgot the name, but so it's described in the literature. You have the same approach has been used to merge three American tech companies. So with the tech companies, there was a merger of three companies, and they wanted to make it one shared structure. But then, of course, each of the companies had their own vocabulary, had their own material, and then they had to agree on a common ontology, because they had to integrate, and in order to avoid to have like three independent entities within the same body, they really made the investment of defining a common language and saying, okay, when you say this, I mean that. And they agreed on a common language, they actually implemented it, and now they work as a single organization. So there are no more duplications of research projects, of administrative tasks, all of that has been integrated. It was a very complex task. Actually, those people were in the same training in New York as I was, so I've witnessed them start the work. It was very impressive. There was another case study described on a German naval company. There's a description of how you can define enterprise standards with the ontology. There are many other cases as well. So for example, here we have a list of, I think it's 50 cases in the slides as well. I'm not going into detail on that, so we focus on the Dutch railway system. where did we go? Okay. So for the Dutch railway station system, we had our top level. Actually, the top level we have for all applications. So it's our top level ontology is Mufe. Why Mufe? Because it's the best described top level ontology we have right now. It's an industry standard. There are other candidates, you have like OntoUML, but that is not used as much in practice. As we want to be practical, we are applying Mufe. Is it perfect? No. Are there other alternatives? Maybe, but we haven't had the time to do the to test whether, for example, all reference content we have is also OntoUML compliant. And I believe that is the work of like 4 to 5 PhD theses at once, because the body of knowledge is huge, and documenting and structuring everything is would be too much for a PhD student and definitely too much for a master thesis student. So how is Mufe applied here? So Mufe provides the structure for all the other models we see here. So that is typically what happens in Mufe. So you have M3 level, M2 level, M1 level, M0 level. As you have only seen UML, you typically have UML models at M1 level. So you make your UML model, and then you populate it with real-world data. That is M0. Have you seen the M levels? No.
So a class diagram, for example, would be on M1.
M1, yeah.
Mm-hmm. So M0 are then the objects as instances of the class model.
Yeah, indeed. And then, so the M2 describes, actually defines the language you use, or you have to use to make your UML models.
Yeah, the associations and the classes and the multiplicities.
Indeed. And if you want to design your own domain-specific modeling language, that is also the level at which you extend UML to define your modeling language that can be reused at M1 level. And then M3 level is then the level or the modeling language, or the model that describes what can be modeled in an M2 model. So that is shared. So that is the top of all GUA reference content. So that is the same for all companies, all applications, including the Dutch railway system. Then our foundational ontology is also the same for every application. So in the foundational ontology, we have these concepts. We have 3 layers: business layer, application layer, technology layer. When we talk about business, we talk about 4 things. We talk about purpose and goal, business competencies, business services, business processes. When we talk about applications, we talk about the applications themselves and their data. When we talk about technology, we talk about technology platforms and infrastructure. But of course, that is very coarse-grained. It defines, domains, although the word has another meaning in our work, but it's not enough to make an actual model. You need more detail. That detail is added here with the core reference ontology. Again, the core reference ontology is the same for all leading practice projects. Here it's visualized as a periodic table, so as in chemistry. So what are the elements we have in all of our applications, all of our models, all of the domain ontologies, all of the task ontologies, all of the application ontologies. What is not shown on this page is that there are also semantic relationships between each of those concepts. Again, as in a periodic table, those relationships are also hidden. You have properties in a periodic table that tell you can combine this atom with another atom to make molecules. You cannot combine that one, or you have to combine them in such a way to have an atoms. So that is hidden here, but it's also there. So you have relationships between them. Of course, you have 91 concepts. If you show all the semantic relationships, you end up with literally thousands of relationships. That is too complex. I've once seen a graph in which each of the objects here is a node on a circle. And then semantic relationships, but what you see is just one big mess. It's not even a maze, it's just too much. But so for each of these concepts in the periodic table, you have a description of the object it relates to and what is a semantic relationship. But that is too much information for this course. So this periodic table, these concepts have been defined by Mark van Roosing. So that was the professor of the training in New York, and he is also the person that has developed this whole standard. So my work is basically structuring things, showing, putting it in the right, at the right level. So saying, okay, this is a core reference ontology, this is the main ontology, this is a task ontology, this is an application ontology, this is how you can combine them. But then the actual content is not my work. So this is the periodic table, and then we do cherry picking. So as in chemistry, we don't use all elements from the periodic table to do what you want to do. So you have organic chemistry, you have other types of chemistry. So you pick a few atoms you work with in your domain or in your task ontology. So then we'll go to the Dutch railway case. So that was what is shared between all applications, all use cases. Here we go to the Dutch railway case, in which we do cherry picking from the core reference ontology, define a domain ontology, define a task ontology, and an application ontology. So then, what was the goal of the Dutch railway case? They wanted to achieve seamless customer experience. Meaning hop on, hop off transport with one payment card without you having to buy 7 different tickets from 7 different vendors. It's just, I need to get from point A to point B. I have my card, I'll get there. And then in the end I will pay. But then the actually distribution of the money is done by system. I don't have to pay for my traject from A to B to one supplier, then B to C to another supplier, then C to D to another. That's not the case. So it's end-to-end transport with one payment. So the implementation of this single payment system had already been done at that time in a few major cities in the world, but it was the first time it would be done in an entire company, in an entire country. And most countries are larger than cities, than major cities. So they had a real problem because it was very complex. So they had multimodal transport. So trains, trams, metros, bus, ferries, all of those had to be compliant to the same system and use the same system. So no more silence, one big system for all. And then for each mode of transport, they even had different transport providers. So then that meant many providers, and so one system for many providers. Instead of having one system per provider, it was one shared system for all providers and for all customers. Which meant that they had to think customer-centric and also role-based. So in most systems, like I sell train tickets, like NMBS sells train tickets to its customers. And they have a customer role, so me, NMBS, sells tickets to customers, and I can replace one customer by another in their models, but they cannot replace themselves. So that was a challenge here. So not only the customer had to be a role, but also the supplier had to be a role. And so you needed to be able to replace the supplier at runtime. Because I could just take a tram from point A to B, a train to B to C, a metro from C to D, a ferry from D to E, and then another tram to, and all of that had to be registered in a single system with a single payment for the client. That means that while you were traveling, the system had to be able to replace one supplier by another, or one transportation provider, provided by another. It was a challenge. So how to tackle the challenge? With an ontology-based model that would then be replicated in all of the companies. So they needed a common language for the system that would then allow each of the individual transportation providers to deal with the system as well. Because the goal was not to replace all IT they had by a new system. That was not the goal. It was just one payment system that would then be able to integrate and interoperate with each of the individual systems. So how to manage the complexity? The answer was with ontology. So I'm taking just one simple example from what they did. So here they really did cherry picking. They just picked exactly one concept from the core reference ontology. Concept of role. If you look at the core reference ontology, role is concept number 25. It's the only one in there. And they developed an entire domain ontology around roles. So what different roles do we have in organizations? In the organizations, so we have different levels from our foundation ontology. Here, I actually discovered that for each of the levels in the foundation ontology, you had roles. So you had roles at organizational level, you had roles in services, you had roles in processes, roles in applications, roles in data, roles in platforms, and roles in our infrastructure. And roles are not only limited to people, the roles of people, but for example, a server can also play a role. A data element can also play a role in different applications. And then they developed that with classification. So role has subtypes. They're called stereotypes here. So we see the organizational role again, we see the service role, and in the organizational roles for people we have subtypes. Which subtypes? We have shareholders, we have citizens, taxpayers, we have executives, we have managers, we have organization owners. At the service level we have service roles. Which service roles do we have? We have service owners, we have service providers, we have service customers. Then a level lower we have process roles, and the process roles, or among the process roles we have process owners, process customers, process workers. Among the process workers there are even many different specializations. They haven't been shown here because it would be too much detail. And for the application roles, actually they had different subtypes as well. We had application owners, application administration, application development, application automated application role, and so on. And among those roles we had even more subtypes. Then for the data roles, again, subtypes, data owners, data administrators, platform roles, platform owners, platform administrators, infrastructure owners, infrastructure administrators, and so on, and so on, and so on. So you develop the levels of detail. But then you're able to go back to the initial role. You know they're all roles from the core reference ontology. And in some models you will see that we will use the stereotypes. In other models you will see that we use the types, or in other models even subtypes. So depending on the level of the model, the application level model you will make, you will use or pick another level of granularity. But then if you use organizational role in a model, in your application level model, then that means that this organizational role concept applies to all its subtypes of That is how we try to establish coherence between the levels. So then it says, okay, when it applies to role, it applies to all roles we have identified. When it applies to an organizational role, it applies to all of its subtypes. When it applies to executives, it only applies to executives and their subroles. And then, of course, this is reference content. So it means once it's described by the Dutch railway system or railway company, other organizations can use this and say, okay, we also have organizational roles, we also have executives, we also have service providers, we also have data roles, we also have, and they can identify additional types and add more detail to this ontology, domain ontology for roles, then communicate that to the Dutch railway system that can then say, okay, those roles are relevant to us or not. So then, what I did not tell you until now is that leading practice has a community open source policy, which means everything you create, all models you make, are open sourced in the community. That means that they can learn from each other. So if someone says, okay, I need a role ontology, they don't have to develop it themselves. They can reuse what has been developed by others and give feedback on it. So they can reuse it, say if it's perfect, they just use it. So they spend, instead of developing their own ontology and a role ontology and spending a whole week on it, they can just read it in an hour, discuss it, say it's good, we use it, and then they have saved time and money. If they say it's not good enough, they develop it, send it back to, they share it on a Dropbox folder, then the Dutch railway company is notified there are changes to the domain model. They can look at it and say, okay, actually, these roles that were added by another company look relevant to us. Actually, this is an improvement on what we had. So that means there is reuse and learning from each other in the community. Through sharing, of course. So then, with this role ontology, they built many different application ontologies. This is just one small example. And in this application ontology, you see the red boxes. Those are concepts from the role domain ontology. So there they have done the cherry picking and they said, okay, we have different types of roles. This is how they fit in our model. You also see other concepts. Other concepts that we can see in our core reference ontology. Those concepts just might have been picked from the core reference ontology as is, or they could have been picked from other domain ontologies that develop those core reference ontology concepts in more detail. And so when that level of detail is useful for this application, we use that, of course. The semantic relationships we see here, so the black lines, can be defined by the core reference ontology. But of course, in certain domain ontologies, you have more detail that can be additional. So that when we pick different objects from different domain ontologies, or for the core reference ontology for an application ontology, we automatically inherit the relationships that have been defined at the level of the core reference ontology, at the level of the different domain ontologies. We also see like numbers here on top of the boxes. So 1, 2, 3, 4, 5, 6. Those relate to a task ontology. Of course, the task element is not visualized very clearly here because this is, like let's say domain view on the application ontology. So the domain concepts are dominant. But here in the bottom you have a legend that says, in our process lifecycle, we have different concepts. We have we start with process analysis. Then we have process design, process development, process implementation, process running and maintenance, and process continuous improvement. And then the numbers on the boxes show which of the concepts are relevant to a certain task. So then in this application ontology, you make the integration of domain knowledge, documented in the domains, and information relevant to a specific task, which is operating a process. But then operating or running a process is not just running. In order to have a sustainable process, you need to do more. You need to do continuous improvement, and your process has an origin. Where does it come from? Actually, it has been designed. How has it been designed? According to an analysis. So this is what the richness that the task ontology brings. So the task here of managing processes actually involves different phases. And you need to think of all the phases, not about running. Just running the application or running the process. So that is something that, okay. So then this is a zoom in on the slide. Okay, so I didn't have to peek actually. This is a view of an integration of different task ontologies. So in here you can see a business model, task ontology, a values lifecycle task ontology, a process lifecycle task ontology, an application lifecycle task ontology. And those concepts can be reused in an application ontology. So and here in the application ontology we saw here, we reused the ones from the green from the process lifecycle. Okay, so the process lifecycle task ontology also relates to different kinds of models. So again, this is a very complex reality, our application ontology. And typically, we only have two-dimensional way of documenting what we have. We make models on paper, and then those models are partial views of a complex reality. So then this documents which objects appear in which models. Why is that important? To make sure that our models are coherent. If you say a business role X does something in it is here a requirements model, then we cannot say the same business model does something else in another model, because then our models become incoherent. So what this matrix shows you, if you say something about a certain object, then you have to make sure that you say the same thing about this object in different models. So this table shows you how you can establish coherence among models you make about the same reality. So that's very useful, and that is a table that you have to use in leading practice to make sure that everything you say is coherent and all views you take in different models are coherent. Then one last thing I want to discuss with you is the structuring orientation. So I already showed to you that ontologies have a structuring orientation. That means that they can help you better understand the complexity of things. So in the Northern Health case, there's the health provider from one of the cases, they have an example of what the structuring orientation can bring. So this is typically the outcome of a business modeling session. This is huge. This is dozens of models about your project. There is a word for this, and that is information overload. It's just too rich. You cannot understand all of it. But here the color codes and the columns and the rows have a meaning. So it means with this very complex reality, the ontology helps you to say, okay, here I can find this information. If I want another type of information, I know I have to look in this column in that row. So then the structure of ontology, or the structuring orientation of ontology, helps you understand those models and easily find what you are looking for. And color coding and so on helps you to find it even better. Yeah, and that is another case also from the Northern Health case. This relates to the table I've shown you here. So here we have an example of a strategy map. In a strategy map, we find instances of 4 different kinds of objects: strategic business objectives, critical success factors, and KPIs. Okay, but those strategic business objectives, critical success factors, and KPIs appear in other models as well. How do I make sure that all KPIs I have in here also appear elsewhere in other models where KPIs are relevant? Well, then I use a table similar to this one to make sure, okay, if I have this in a strategy map, then I also need the same concept in those other maps. And then you look on the same line where in which column you see a 1, 2, or 3. So then again, there's an application of the structuring orientation of ontology. Summary. So GUI and leading practice, or the GUI and leading practice ontology, uses the structuring orientation of ontology to slice and dice the complexity of reality. So both visually representing and with the layers. So for the visual representation of the outcomes and for the layers in our ontology stack. So then the ontology stack itself promotes reuse of reference content. So what is in the core reference ontology should be reused and visible in the domain and task ontologies. What is in the domain and task ontologies should be represented in the application ontologies. When I build an application ontology and I see something is missing in a task or a domain ontology, I update the task and domain ontology, communicate that to my peers that can then learn from me. So this reuse and learning is actually the strength of the GUI and the LEAD approach. GUI and LEAD has been successfully applied in industry. It has academic support through the Global University Alliance, and it has industry support through leading practice. A leading practice is the community open source community where all people that have done the training and are certified to use the content and means are able to understand the complexity of everything they find there, have access to what others do with the same content. Okay. So thank you for your attention. There are 60 more slides in this presentation. It will be made available to you, and in there you find more information. So you find more papers about these topics and more models that explain to you how this works. So for example, this is a bibliography of relevant papers. These are examples of how you use classifications to develop more detailed application ontologies. So for example, if I'm thinking about smart applications, what do I have? I have different types. I have intelligent personal assistants. I have artificial intelligence. What do I have as part of the intelligent personal assistants? I have voice query assistants. I have natural language apps. I have and so on and so on and so on. So this is reference content that is available in the community, and then if you say, okay, I want to implement a payment service, then you don't need to have a meeting with dozens of suppliers that tell you what types exist. You can just pick the reference content and say, okay, this is what I want. I don't want this one. I don't, but I do want the other one. So that is available there, and it saves you lots of time. It's all information. You don't have to recreate or duplicate because it's available. It has been updated by your colleagues, and if you say actually there is one kind missing, you just add it, and then your other colleagues in the community can use this as well. What else? Yeah, these are slides about the visualization. So UML is very straightforward. It's like black and white boxes. It's great for people in informatics, but actually, if you UML only uses 2 dimensions of the 5 visual dimensions that are available to us. So what else can be used to make models that are easier to understand is described by Daniel Moody. And so actually what we see here in the leading practice content is an application of that theory. So then you can use texture, you can use color, you can use all kinds of stuff. You can visual spacing can be used to make your model more easily understandable. So then that has also been applied here, and there is much more. So this is an example of a UML model of or an UML equivalent of a leading practice model. So we have the domain-specific modeling language, but if you wanted an UML, it's possible. So since it's MOF-based, it's easy to make the translation. You just get rid of the visual, let's say the eye candy, and then you have this. And I can go on for many more hours, but I think that is the end of it. Thank you for your attention.
Thank you. Thank you, Wim. I think this is all we have time for right now. In our preparations, we came to the conclusion that there is so much material about Hua at the moment that we could easily fill 2 weeks of sessions or 3 weeks even.
Yeah, a whole course,
The whole course could be. And so, this was meant to be an illustration of one of the topics that can be chosen on the university or academic side. The next step is that we meet next week, virtually or in physical terms, to choose which group will pick which topic. We don't have to physically meet. If you just send in by Friday, this is my group and all this kind of stuff, it's okay with me. On the other hand, I'm available at 2 p.m. as well. So it's up to you to see how that goes. Okay, so one or even more groups can pick this topic, I think, as it is that large. So I wanted to point out, I don't think it's necessary to have only one group max or something like that. You mentioned already there are 4 or 5 PhDs, well, specifically on the topic of comparing with the UML.
But that is very formal. I'm not sure this is what's...
No. No. The topic of the paper is fixed. They have to look at something new and evaluate whether an organization of choice, when they graduate in about a year or so, would rather or not use that technology from now on. And they have to use material in their courses, academic literature, more applied things, experts from industry, which again makes this a very nice topic. To deal with that. No. They're not going to do the meta level stuff in the Capita Selecta course. Okay. Questions at this point in time? How are the internal deliberations going? Are the topics becoming clearer, the interests of everybody? Are we still without first ideas at the moment? Pauline mentioned the topic last week already. Yeah, what about the others? This is progressing. Yeah, a little bit. Still 1 week to go. As I said last week, for me, the deadline next week, Monday, is not necessarily completely formal, but it was chosen to be relatively early in the course to avoid you losing time by not setting the topic early.